Hi everybody, welcome back to the Feynman technique. Today I've got one that I got off of the channel Maths 505. Um, he used contour integration, which I'm not a fan of. I'm going to be using differentiation under the integral sign, aka Feynman integration, along with a previously derived formula. The previously derived formula we're going to be using is this, that the integral from 0 to infinity of 1 over x to the t plus 1 dx is equal to pi over t times the cosecant of pi over t. I will try to remember to link in the description to the video where I showed this. Um, but for this problem, we're just going to be taking this for granted. And I'll just say for the restrictions on t, we'll place restrictions on t such that this integral converges. If this integral converges, it converges to this. All right, and I won't go any further than that on the restrictions on t. We'll just say that for whatever values of t this integral converges, it converges to this. All right. So to get started on working on this, what I'd like to do is define an integral we'll call f of a and b to be equal to the integral from 0 to infinity of, let's see, let's do x to the b over, no, we'll do x to the a over x to the b plus 1 dx. All right, and then we're going to make a substitution. We're going to let x to the a dx be equal to du. And that is so we can make this just a 1 over something du, which is the form we want in order to be able to use this formula. So if we start with x to the a dx being equal to du, all we do is anti-differentiate on both sides to get x to the a plus 1 over a plus 1 is equal to u. And then what I'll do is I will multiply both sides by a plus 1 to give us this. And then I will raise both sides to the 1 over a plus 1 power. 1 over a plus 1 power. And that's just going to give us x. All right, now we don't need to solve for dx because we already have a to the x dx being equal to du. But what we do need to solve for is x to the b. So x to the b will just simply be this entire thing raised to the b, which just multiplies the exponent by b. All right, so now we can define our f of a and b like this. Well, we initiated our substitution so that this x to the a dx will just be du. And our x to the b right here, that's just this, so we copy and paste it in. And now what I'd like to do is say that v is equal to a plus 1 times u, implying that du is going to be 1 over a plus 1 dv. We'll plug that into our substitution. And by the way, our bounds of integration don't change for any of these. Okay, so let's see, this a plus 1u is just v now. And our du is 1 over a plus 1 dv. And we can bring out this 1 over a plus 1. And now you'll notice that this is exactly in this form. So what we'll do is we'll say that this implies, or we'll say that this is equal to 1 over a plus 1, and then we will copy this part over here, except our t is no longer just a t, it is b over a plus 1. So if we plug in b over a plus 1 for this t, we'll get b over a plus 1, and then this a plus 1 will cancel this a plus 1. So we still just have pi over b. And then if we plug in b over a plus 1 for this t, what we end up with is an a plus 1 up top and a b on the bottom. All right. So now we've shown that our original f of a and b, which was this, is equal to this. All right. Now I want to make one more modification. Let's make f of a, b, and c being equal to this. And we will insert the parameter c right in front of that x to the b. All right. And now let's let cx to the b equal u to the b. All right. Well, that implies what? Well, let's bring this c to the other side as a c to the negative 1. And then we'll take both sides to the 1 over b power, giving us x on this side and a u times c to the negative 1 over b on this side. And now we can solve for dx. This is going to imply that dx is just c to the negative 1 over b du. And we will plug that into our integral. All right, so applying that substitution, well, x to the a is going to be this thing raised to the a power. So that's going to bring an a upstairs, and we'll just have a u to the a there. And we can bring this outside our integral. We defined cx to the b to be u to the b. And our dx is just this part right here. And we can bring this c to the negative 1 over b power outside, since it's constant with respect to u, making the thing outside the integral just c to the negative a plus 1 over b power. All right, and now this, let's see, we can replace our dummy variables. We'll just put x, x, and x. And this is exactly our original f of a and b. You'll see that's right here, which we know is equal to this. So we can just put that right there. All right. So now we have our original f of a, b, and c, which is this thing, equaling this thing. Okay. And now actually what we can do is we can plug some values in right away to get it closer to our original I. All right. So what could we plug in? Well, let's see. We could let a equal negative a, right? Because we actually have a negative a in our original integral. And I'll put that up here. I is equal to this, but it's also equal to this, x to the negative a. All right. So if we wanted to make this more like our original integral, we let a equal negative a. So we'll just do that. If this is true, then this is true. And then we'll put a negative a there, and we'll make this a, or 1 minus a. All right. And let's distribute this negative sign. So that's going to be c raised to the a minus 1 power. All right. Now, also, we would like this b to actually be a, let's see, what do we want? What do we want it to be? Not sure yet. Let's go ahead and take care of this c. We want the c to be a negative 1. In fact, we want the b to be 1 and the c to be negative 1. So let's do b is equal to 1 first. All right. So if we let b equal 1, we have that. All right. b is 1, b is 1, b is, and now we want our c to be a negative 1. So place that with a negative 1. All right, so now we have 1 minus x on the denominator. So now we're fairly close. Let's see. Now all I think we need to do is just take a derivative on both sides with respect to a, and that will allow us to recover that natural log x. So on both sides of this, we will differentiate with respect to a. And of course, we can use the Leibniz rule for differentiation under the integral sign, aka Feynman integration, to bring this derivative inside as a partial, just like that. All right, and now let's actually evaluate the derivative with respect to a of this. Well, our 1 minus x on the denominator is constant with respect to a, so we're just going to end up with negative x to the negative a natural log x over 1 minus x. And now we have to take the derivative with respect to a of this, which is a bit more challenging, although you just follow basic differentiation rules. I'm actually going to plug this into online integral calculator really quick, just to make sure I don't make any silly mistakes. But it's a straightforward calculation, and it looks like I already have it pulled up here. But let's put it in again. So we want the derivative of that thing with respect to a. I'll click go. And it spits this out right here. So we will copy it and put it right here. All right, now let's multiply both sides by a negative to get this. Okay, so technically we're done. This is the integral we were trying to solve, but we definitely need to clean this up a little bit. As you can see, we have some nasty stuff in here, like the natural log of negative 1, which we can't really... Well, that's no good, but we can manipulate this so that will actually go away. This natural log 1, negative 1 actually cancels out, and I'll show you what happens. First of all, well, let's just copy this down here and clean this up a little bit. Let's see. Natural log of negative 1. Well, negative 1 can be written as e to the I pi. Principal value anyway. And then natural log composed with e just gives us I pi. So this is just plus I pi. All right. Now there is an identity for this. Cotangent of pi minus pi a, I believe that is negative cotangent of pi a. Let's see. Yeah, it is. Okay. So we can replace this cotangent pi minus pi a, which is just this thing when you distribute the pi, with a negative cotangent pi a. So let's do that. So that's just going to give us a negative cotangent pi a. And we can't forget the negative sign there. All right. Cosecant pi minus pi a is just cosecant of pi a. So pi a. All right. So we're doing a little bit better now, but we still have this imaginary thing in here. But that's not going to be that big a problem, and I'm going to show you why. First of all, let's rewrite this negative 1 as e to the I pi. E to the I pi. And then we can just say that whole thing is e to the I pi a. All right. I think it's time for a new line. So let's copy and paste this like that. And then what I'd like to do is divide this entire thing by sine of pi a. So I divided it by sine pi a, so I have to multiply it by sine pi a. Oh, and really quick, let's go ahead and factor out this pi. So we have pi squared, and then I'm going to put this on the other side. All right. And then I can't forget to also multiply the top by sine pi a. I sine pi a, and then multiplying cotangent is just going to give us cosine pi a. And then to make this just a little bit clearer even, let's introduce another negative sign and actually make this minus I sine pi a. And we can put this cosine pi a in front of it. All right, now you'll notice that this right here, this is just e to the negative I pi a. That's Euler's formula. Cosine e to the I theta is equal to cosine theta plus I sine theta. And if we have our theta equaling negative I pi a, or pi a, this is the result. So we can rewrite that cosine pi a minus I sine pi a as just e to the negative I pi a. And then you'll notice this multiplied by this is just going to give us 1. That cancels out nicely. And then this cosecant pi a, we can bring to the denominator as a sine pi a, just giving us sine squared pi a. And that is it. That is the solution to this integral. I believe Math 505 got not a different answer. They have to be equivalent, but he wrote it in a different form. I like this form a little bit better. I think it's a little bit cleaner. We could even write this as negative pi times cosecant pi a all squared if we wanted to, but I'm going to leave it like this. All right, guys, hope you enjoyed that, and we'll see you next time.